In this lesson, we will analyze a few real circuits that I have used in audio processing. These circuits should be easy to understand with the knowledge we already have. I have used these circuits in my modular synthesizer, which is a project that I have worked on for the past years. But first, let's try to understand what a synthesizer is. A synthesizer is a machine that can be built with different circuits, and its objective is to generate sounds. If you have listened to any song from the past 40 years, most probably you have listened to a synthesized sound. The kind of sounds that synthesizers produce can be drums, bass, strings instruments, and even voice effects. A synthesizer can be used to mimic the sounds of real instruments like flutes, violins, and pianos, or even to produce completely new sounds. From the electrical engineering point of view, the synthesizers are very interesting because they can be built using all analog components. Synthesizers are composed by larger subcircuits like oscillators that produce sound waves. Then these waves are manipulated by other elements like filters, which remove frequency content, or envelopes that change the amplitude of the sound. There can be other type of modulations that change the characteristics of the sound over time. In this image, you can see a basic architecture consisting of two oscillators that are added and then they are passed to a filter in order to remove some of the frequencies, and then the amplitude is controlled by a signal that is generated by an envelope that defines what's going to be the amplitude. So with this simple architecture, you can create like a variety of sounds. There are two main kinds of synthesizers. The ones that we can call fixed architecture synthesizers, which is like the one on the left. You can see that it has piano keys and multiple controls to change the characteristics of the sound. Internally, it has a somewhat fixed architecture, like the one we saw in the last slide. On the right, we have a modular synthesizer. Modular synthesizers are built by different modules that can be from different companies, but they are all compatible. As you can see in the picture, the modules are physically connected by cables. In this case, the user can decide the whole architecture of the machine. I have designed and built many of the modules that you see in the modular synthesizer. In this lesson, we will check some of the utility modules that I have built using simple op-amp circuits. The first circuit that we are going to check is an audio mixer. The purpose of an audio mixer is to combine multiple audio signals, which are voltages, and it produces a single audio signal. This is useful, for example, when you have multiple sound sources like drums, guitar, and voice, and you want to combine them so you can hear them in a pair of speakers. This module you see on the screen is my mixer module, and it can combine up to 6 audio signals, providing volume control for each signal individually. For educational purposes, we are going to analyze a reduced version of the mixer that has only 3 channels. Here you can see the diagram of a 3-channel mixer. The module is composed of 3 main parts: the volume control, an inverting adder, and an inverting amplifier. Let's analyze it from front to back. At the end, we have an inverting amplifier with a gain of -1. The only purpose is to invert the audio signal produced by the inverting adder. The inverting adder combines 3 voltages. As you can see from the resistor values, all of them are the same. Therefore, each input has a gain of -1. The volume is controlled by a potentiometer that acts as a variable voltage divider. If you remember, the voltage divider is affected by the circuit connected to it. In this case, we have a 47 kilo ohm resistor connected to virtual ground. Let's see how this affects the voltage divider and determine if it's bad or good for this circuit. In this diagram, we can see the equivalent circuit of the volume control. The potentiometer is split into 2 resistors whose value is dependent on the position. When one resistor increases, the other one gets smaller, and the sum of these 2 resistance must be constant. In this case, the potentiometer is 10 kilo ohms. We can capture this behavior with the following formulas for the upper and lower resistors. And here you can see that changing the variable for the position, one of the resistors increases and the other one is decreasing. The middle point of the potentiometer is connected to a 47 kilo ohm resistor, which is connected to virtual ground. We have already analyzed this circuit in the voltage divider lessons. What we did was to combine, in this case, resistor 2 and the lower part of the potentiometer into a single equivalent resistors because they are in parallel. Then we can use the voltage divider formula to calculate the voltage at this point. After replacing the numeric values, the formula is simplified to the following. Let's create a plot to see what's the gain of the circuit depending on the position of the potentiometer. Here we can see a plot with the gain of the volume control circuit compared to the ideal response. In this case, I wanted to have a linear response. That way, when the potentiometer is at 12 o'clock, the gain should be 0.5. We can see that the control is not perfectly linear. However, the result is good enough for this circuit. One way of improving it will be to make the 47 kilo ohm resistors higher, for example, 100 kilo ohms. The following plot shows the simulation results of the mixer when we use as input 3 different sine waves. In the plot below, we can see the waveform they create after combined. That's all for the mixer. Now that you know the basics, you can extend it if you want to add extra channels. The next circuit that we're going to analyze is called attenuverter. The name is a combination of the words attenuator and inverter. So it is used to attenuate a signal, but it can also invert it. In the right, we can see a picture of the module I created, which features 4 attenuverter circuits. In the plot, we can observe the behavior. On the top, we have the input signal in blue, which is a sine wave with a value that goes from 0 to 1. In orange, we can see the position of a potentiometer. 0 represents the potentiometer being fully counterclockwise, and 1 represents full clockwise. We can see that when the position is 0, the output signal is inverted. As we approach the middle position, the amplitude decreases to 0. As we continue, the output becomes positive. This circuit is very useful to adapt modulation signals coming from generators. Now let's see how the module is built. In the diagram you can see the circuit. We have what looks like an inverting amplifier connected to a voltage source V1, but the non-inverting input we have a potentiometer connected. On the top, there is a block that provides a control signal to change the position of the potentiometer during the simulation. If you look at this circuit carefully, you may notice that it looks very similar to the architecture that we have already analyzed, the subtracting amplifier. Here you can see the diagram of the subtracting amplifier, and here is the circuit of the attenuverter. Below you can see the formula that we obtained for this circuit. And if you look carefully, the attenuverter looks like this. The main difference is that the voltage V2 is the same, is connected to V1. And the resistors R2 and R3 are replaced by the potentiometer. So the ratio of the voltage divider can be changed by this potentiometer. We can derive the attenuverter formula directly from the subtracting amplifier formula. We have to replace the voltage V2 by V1, and the resistors 2 and 3 are replaced by the model we used in the previous example for the upper and lower resistor values of the potentiometer. Then we replace the numeric values. And after simplification, the formula we obtain for the gain is the following. It is basically twice the position of the potentiometer minus 1. If we plot this equation for the gain, we can see that when the position is 0, the gain is minus 1. And when the position is 1, the gain is 1. The first time I saw the circuit, it took me some time to understand it. But seen as a subtracting amplifier, the behavior is much more obvious. The next circuit that we're going to analyze comes from a distortion pedal. This type of distortion was used in a famous guitar pedal called the Proco Rat. But in order to understand it, we need to learn a little bit about a component that we have not studied yet, the diode. Diodes are semiconductor devices that, in a nutshell, They allow the flow of current only in one direction. In the diagram, we can see a diode connected in series with a resistor. The input voltage is a sine wave of 2 volts of amplitude. The simulation results show the input voltage in orange and the voltage of the resistor in blue. We can observe that when the input voltage is negative, the resistor doesn't see any voltage because the diode is blocking the current. But when the voltage is positive, the resistor receives part of the voltage. It's not exactly the input voltage. This is because the diode takes a little bit of the voltage when current flows. These voltage drops depend on the diode. A general purpose diode will drop around 0.6 volts. Now let's take this circuit and change the position of the components. The circuit is the same, but now the diode is connected to ground. The simulation shows the input voltage in blue and the diode voltage in orange. We can clearly see that when the input is negative, all the voltage is in the diode. However, when the voltage becomes positive, first it follows the input voltage, but then it starts getting rounded until it doesn't rise anymore. Any voltage larger than the diode drop gets clipped. One nice thing with this circuit is that the voltage is gradually clipped. We can see the roundness of the sine wave before it reaches the maximum. This is usually called soft clipping. The guitar distortion relies on this effect of clipping the audio coming from the electric guitar. However, the audio signal is bipolar. It can be positive and negative. What we need is a way of clipping the bottom part of the signal when it is negative. The easiest way of obtaining symmetric clipping is by adding a second diode connected in parallel but pointing in the opposite direction. This is shown in the diagram. When the voltage is positive, the diode pointing down will clip it, and when the input is negative, the diode pointing up will clip the input. This result is shown in the plot here. We can see that the voltage in the diodes clips the input signal symmetrically. If the input is very large, the clipping will be aggressive, but if the signal is low, it will only round the signal a bit. Let's get a comparison between a sine wave without distortion and then the same sine wave with distortion. This is without distortion and this is with distortion. The distorted sine wave has more harmonics and it sounds brighter and louder. Let's listen to another example. In this case, it is a group of sine waves forming a chord. Without distortion, it sounds as follows. Now let's listen to the distorted sound. This sounds closer to what we hear in an electric guitar with distortion. In order to control the level of distortion, we need to control the amplitude of the input signal, and we already know a circuit that we can use for that task. Here we can see a slightly simplified version of the distortion circuit. We can observe the pair of diodes we explored before. They are connected in series with a resistor of 1K. The voltage is provided by a non-inverting amplifier circuit. The interesting part of this circuit is that in place of the feedback resistor, we have a potentiometer. If you remember the formula for the non-inverting amplifier, the gain is 1 plus the ratio of the feedback resistor and the resistor R. In this case, the RF it's a 100 kilo ohm potentiometer, while the resistor R is a 1 kilo ohm resistor. This means that at one of the extremes, the amplification will be 101x. This voltage will be limited by the output of the op-amp, which, if you remember, it cannot provide more than plus minus 12 volts because of the power supply. Then the signal will be passed to the diodes to clip it even further. When the potentiometer is 0 ohms, the circuit becomes a voltage follower with a gain of 1. Then the signal will be passed without much amplification to the clipping diodes. The guitar pedal has other stages like a tone control and a buffering stage, but in this course we will not analyze them. To summarize this lesson, we explored 3 circuits that have a practical application in audio processing. The first one was a 3-channel mixer which was built using an inverting adder circuit. The second circuit is an attenuverter, which is a module that is very useful in modular synthesis. This circuit is built based on the subtracting amplifier we studied. Last, we learn how one of the classic distortion pedals work. We learn a little bit about diodes, and we learn how to control the distortion level using an inverting amplifier of variable gain.